And for this demo, I have a UCMX. I will open up a job. And actually, this job I will now want to process with YELO. I put the YELO in small yellow icons, so it's easy to find on my toolbar. And actually, I have here, this is the module, and I will explain the module in detail. But first of all, let me just say, okay, because actually people, they have just normally they have their parameter sets, how they can check, because they want to have a board in a certain technology class, like 80 micron, 100 micron, you know. So actually I can put this board in a certain class, all the values will be filled out, and I can just say, okay, verify and adjust, and it will start processing. So that's actually how it normally works. In this case, I have a set where actually we can show all the repairs that YELO does in a very good way. So I use this set of data now. And the interesting bit is first, like, okay, I can say, okay, with these values that I have, can I verify the data? And actually, I just press the verify button, and now all the parameters that I put in here will be used for a DRC. And it says actually now, okay, I did my DRC. I have over 2000 issues on this board with these DRC parameters that you gave me, which is obviously quite a lot. So, and if I just look at all the positions where I have issues, it is actually, well, it's every white dot that you see is an issue. So some are distance issues, some are too less copper, some are, so there's all kind of issues actually that that we have on this board. But of course we have YELO, so and YELO is actually there to to solve all those issues. I mean, that's why you should use it in the first place. So I will first start the optimization, because I will do it on the whole job in one go. And while it is optimizing the whole layout, I will explain the interface. Okay, so I press the verify and adjust. You see it starts also solving faults. So this is actually now where we can say, okay, I will start with the upper part of the window. You can actually see, if I move this a little bit to the right, you can see that the window is made out of like 4 parts. So you can change your parameter sets. Then you have the verify parameters. So this is your DRC parameters, if you like. And below that, you have the adjustment parameters. So the adjustments that I allow him to do. And below there, we have some, well, some toggles that we talk about later on. But we start with the verify parameters. And actually, so the first thing that we have over here is the annular rings. So I have a drill hole, it hits a pad, and how much is the annular ring that I need. And actually I can specify that for different kind of holes. So I can specify this for mechanical vias, for laser vias, component holes, mechanical holes. And very interesting, I can say, okay, I have a minimum ring that I need for my production, but I can also specify an optimum ring, like, okay, 50 micron is good, but 100 micron is a lot easier. But of course, it's always what is possible. So if the optimum ring is not achievable, it is allowed to go down to 50 microns. Then I can set what kind of clearances I want to have on my board. So pad-to-pad clearances, pad-to-trace, pad-to-regions. So there's regions are copper pores that you can also see here in the background, you know, the copper planes. And I have the same also for trace-to-trace, trace-to-region, the plated holes, the non-plated holes. And I have also clearances to the outline. So I can also say my traces should have a certain distance to my outline of the board and the region as well. I have a plated hole to plated hole clearance that I can set. The same net clearance, which is quite nice if you have some coils and stuff like this on your board. Then for my planes, my copper planes, I actually can set a minimum copper width. So I can say, okay, in this case, I want to have an 80 microns for as a minimum copper on in my planes. I want to define a minimum copper region size. So I have here 0.2 millimeters. So actually every copper that is smaller than 200 micrometers will be removed. So obviously it should be it's standalone copper, so it's not connected to anything. But sometimes in your planes you have these little dots. Actually, if you have very keen eyes, by the way, I see that's by coincidence. I have over here, I have a very little red dot, and I think afterwards this little red dot will not be there anymore. And last but not least, we have the in-plane clearance of 0.3. This is actually for my, well, I will show this obviously also later in my plane layers, but this is actually giving the clearance that I need between, well, I'll show it to you later. Let's because actually it's maybe not so easy to explain, but I mean a picture always says more than 1,000 words, so we'll go to the picture later. Then we go to the second, the adjust parameters. So that would be this. I put it just in a little picture, so it's a little bit bigger. You can see it a little bit easier. It's a little bit easier to read because the window is of course quite big. Now in this adjust parameter section, you find all kind of ways that actually the repairs can be done, or for the different situations that are found on the board and the repairs that are fitting to this. Now it is like this, that actually, for example here, I did not allow an SMD pad shave or SMD pad neck repair method. I also did not allow traces to be necked because normally this is the kind of repair that for sure would you would require an okay from your customer, you know. So first I try to see if I can solve all my issues without these two. However, if your customer says it doesn't matter, you click everything. I mean, that's okay, you know, you can do this. So, and actually, what of course we are trying to do is to find the best solution, you know. So actually we want to have the least number of possible adjustments, and actually we prefer always the methods that are at the top, and actually we will go down. So actually the SMD pads and traces would be the last ones anyway. So if I would tick them on, and there would be no reason to shave SMD pads because I can, for example, also move a trace, it will move the trace, it will not shave the SMD pad. Okay, so there is an order here, and actually we have an artificial intelligence algorithm in the background, and it will just use the first approved methods, and only if these methods fail, it will then unlock the deeper approved methods, you know. So it will find its way, and it will always try to achieve so the solution with the least possible number of adjustments. So this is actually about the adjustment parameters. So I already said we have here, but I didn't make an extra picture for this. I have here a few extra toggles, like I have a backup of original layers. This is of course very useful. I mean, afterwards, if the repair is done, I will have for every layer, I will have a backup, and I can actually then very easily see the changes that have been made. So that's actually a useful feature. I have here a toggle activate drill layers hitting active copper layers. This is actually, I mean, I think I can move the window. No, I cannot move the window around. But actually we have, of course, in this PCB, there is a drill layer, and it's been activated now automatically because actually we also like to change it. I mean, we actually set the mechanical via holes, they can shrink. So obviously I also want to have my drill file changed if needed. Okay. And the last is actually here is run auto markup on the copper layers. Well, what does this do? Well, actually, if you want to run the copper adjuster, you need to do a few small preparations on the data. It is not much, and I can show it also. I will also show it, those preparations. Yeah, so, and actually if you toggle this button, it will automatically mark up your PCB, and so you will be able to run YELO right away because everything goes in automatically. But on the other hand, you have also a possibility to do this manually. And well, I'll talk about those later on. Okay, so yes.
Can I interrupt a little bit?
Of course.
I have a question here, and I think it's very important for everybody in the audience. Maybe
Yes.
you can explain a bit how they would know which values to use. How do they get the parameter sets, you know?
Yes, well, I mean, there is. Thank you, Sylvia. Yeah, that's a good question. Well, you have different ways, I think, to set the values that you have. I mean, you normally always use the parameter sets that I already showed in the beginning, and you will have the different classes, you know, so where actually your customer says, well, I have a board here and it is in a 100 micron technology class. And I mean, you can of course believe this customer and just say, okay, it will be 100 micron, and actually you can say, so I will, maybe you want then to try to get the whole board in 120 micron because it will make it much easier for you to produce. Okay. Otherwise, however, I know a lot of people who say, well, here I have my design data, and my design data is actually 100 microns, and you do your DRC check, and it's not 100. You have 95, you have 90 microns. So actually, the customer says it's 100, but it's actually not. And you can then, of course, use YELO to say, okay, I set my parameter set for 100 micron, and I let it run this way. It is also very well doable to use the results of the integrator, the other product that we have. Well, it should of course not be something that well, it is a possibility. Integrator will give also all the values. It will do your complete DRC, and you can use those values. Like integrator says it's 95, so you say, okay, I try to get it to 100. You know, so that's then you have already your automatic DRC done. You know, so I think this is quite a good way to do this, and you can easily then use your well, your parameter sets that we have over here. Okay. In the meantime, you can see that we have a lot of new help files. So I will, if I move away the window and also this window, you can see that all my files, I have them now also as an original over here. Okay. So now we will see what kind of optimizations integrator actually did. So we have this whole PCB here. I will click away. So actually it says that we have found no errors in the net compare. So we will do a net compare, obviously, so that the electrical information stays the same before and after the YELO process. So, and actually what I will do now is that I will first take you through the different optimizations. After that, I will show you, because you already saw here, you have this little window, like it says there's still 822 violations. So we'll have a short look what this is all about. Like, shouldn't it go all automatically? Well, it actually does, but so we'll take a look at that later on. But first, let's just go through the list and see what kind of repairs YELO actually did. Okay, so we have something like here, the mechanical holes. Okay, so and if I actually look at my data, I have, for example, at this position, I have a hole and I have some copper. Now, interesting enough, if I actually would put my my drill layer, my original drill layer on top, you can actually see that my original drill layer, which is now kind of a sandish color, it's a little bit bigger than the hole that I have now. So it actually, it's made the hole slightly smaller. But also very interesting is that if I take my original layer and I put that one in green, you can actually see that my original layer, that it also, in this case, expanded the pad. So actually we already have two repair methods on this one situation. So we have here the mechanical via holes that are now made smaller. And what we have is a drilled pad that has been expanded. So here you can already see that we try to make with a minimum on impact on the design, but still achieve the rules that you want to have. So the values that you want to have. Okay. So if we take a look a little further, for example, in this position here. Okay. Here you can see kind of the same, you know. So actually these two holes were via holes, and what you can see is here the original pad. We enlarged the pad here quite a lot. We did not enlarge it on the other side because it's a huge ring already, you know, it's very big. But this pad we enlarged, and actually afterwards to ensure that we have the correct clearance, we shaved we shaved the surplus amount of copper, you know. So actually we have now, this is a perfect situation. So we have the biggest ring that we can get, and we still have our clearance. Okay. Then we have something, I mean, what we already saw here, the outline clearance to region, for example. Okay. So if you can see it at the bottom over here. So if I take a look, I have a before and an after. The little gray line that you see is the outline. So you can see that before it was actually almost on top of the outline, and now we have 0.3 millimeter clearance here. Then we go on and we go to a little bit, so we go to this position over here. Okay. Because actually, I mean, it was of course going through the list. What we're actually seeing here is the shave of the regions. Okay, and the region can be shaved against a lot of against a lot of objects. So we have already seen the outline. Now we see a shave to the pad or a track. And if we go a little bit further up, we can also see the shave. For example, here you can see that we had a plated hole, and we also shaved away the copper here around the plated hole. Then we are getting to an interesting part of the PCB because, well, we'll see it over here. You can see the green layer. I will maybe hide the red. This was the original, the green layer. And you see actually that the clearance here around all the pads, I mean, it's not nearly enough. I want to have 0.3, and I think this is kind of 0.1 or 0.15, something like that. And actually what we made out of this is this. So I will hide now the green layer. So it looks quite different. So we have achieved all our clearances here, but obviously I have two drills that were actually connected to the plane. And obviously this connection is not something I want to lose, because then obviously the netlist would change, you know. So this is actually also what I see over here. I have a plane optimization, and so I allow it to adjust, and I also allow copper width removal if the netlist is preserved. Okay, so here I see that all my copper has been removed, but it doesn't change the netlist. Of course, if I would remove this, it actually would change the netlist. So this is something. Yeah, well, it's a repair to keep the netlist in the same condition as it was before, so that we don't have any netlist errors, and your board will still function as it should. Then, furthermore, we have, for example, this situation over here. I will put the original layer in green again. Okay, because actually now we have seen the plane adjustments. Now we're going to the traces, and the traces, actually you can see that this one actually has remained on the same side, because actually here it could shave away some of the copper plane, but the other ones have been moved all a little bit. But in the end, of course, I have a nice bundle with the correct clearance values. So, and if I go a little bit further, I mean, also this, we have a possibility to actually to cut the track. Oh, this is not the correct position. Let's just quickly see. Over here it is. So actually what you see over here, that this track was going too close to the pad over here. And actually you see now with, you know, it's again the minimal change that you can make, but it's enough to respect now all clearances. So this is yes, a very nice and subtle example. You know, if you see it like this, well, it looks like it was intended this way. You know, so that's actually what we over here. We have something similar. You know, you have a few pads, and actually the track before it was, if I put it also in green, before it was just a straight track, and it would have clearance issues to this pad and clearance issues to this pad, but now it's been broken up in a few pieces, and it actually respects all the clearances now. So actually, if I don't want the tracks to be broken up, I can also say I don't allow the splitting. You know, so I have an option to switch it on or off. So then for the track move, you can also see already here a little bit on the bottom that it's also being moved away from the outline again. You know, so that so the tracks are not being cut away. Of course, they are being moved away. That is by far the better solution. And then we get actually down here to the via pads and the component pads. So we have a few via pads up here, like over here. And here you can actually see that we have now enough clearance between the two via pads. So the via pads are actually shaved. And for the component pads, we have some over here, like over here. Okay, you can also see this track. Actually, it was too close to all these pads. So these pads have now been shaved. And I mean, that's of course quite nice. That's here, down here, you can also see still a result of the splitted track move. Okay, so I mean, if I would show only the new design, it really is a very nice repair. So we still have something that we have, so what we did not do, and actually now we're getting to what I said before. So first, these are the different methods that I've shown now. I must admit, I forgot one, because actually we have also some repairs on the planes. I mean, you have, I mean, also, for example, over here. I mean, now you say, okay, what kind of repair is this? I mean, I don't see anything here. Well, that's exactly the point. Because if I look at the original, I see here little copper dots that I actually don't want to have in my production process. Okay, so this is something that has been removed automatically. Another thing actually, which has been done, which is also a very nice improvement, is that you see over here, and now the question is, of course, that you say, okay, what do I see over here? Well, you can see if you have sharp edges, that actually the copper will be rounded. So if I take this away, you can actually see that this has been nicely rounded. Here we don't have such a sharp edge, so this is still okay. Here we have it nicely rounded, you know, so that's actually a quite nice improvement as well. Okay, so then what we also do, and what I also talked about, which would be on the first layer again, like over here, we have something, and actually this is quite easy to see. I talked about the in-plane copper width, this one over here. Okay, and of course we can ask ourselves now, did we have some improvements in my copper planes? So actually what I am going to do now is I'm going to pop out the aperture manager, like over here, and I'm going to look down here, and I can see that actually also I have some new apertures that YELO added. And I see actually over here that I have an aperture copper width. Okay, and this is actually the aperture that we've used for the in-plane copper width size. And I can, of course, I can select this. Okay, and I will pop this just back in. And I can see now very tiny white dots. I mean, you have to have very good eyes for that, but well, I can actually see them. And these are actually now the places where we enlarged the copper a little bit. So let's just take a closer look, like over here. You know, you have over here on top, we have some copper that was smaller than 80 microns. And here we have also something that was smaller than 80 microns. So let's zoom in a little bit more. Okay, so this is actually our repaired layer. The original layer looked like this, where we have actually now less than 80 microns, you know, because actually what we used for the drawing, we use 80 microns, so this would have been 50 microns or something like this. Okay, this is also, again, the least invasive method, you know. I mean, otherwise I could of course also say I take it this bridge complete away, but it would be more invasive, so we choose actually then to use this repair method. Okay, So what we actually, so these are the repairs that we do. What we of course still have, so I will just deselect everything now. So, and I will go to a total view and I will do it like this. And actually what we still had, what I was talking about, like there's still what looks like some issues, but actually if we take a closer look, there are no issues at all. For example, I have pet to track issues. So, and if I just take a look, I will go to total. It's again where the white dots is. We have violations of our rules. So if we now take a closer look, actually, what we see is that we have over here, we have a situation where the clearance between a pet and a truck is not enough. And actually next to that, we have another pet. So it's not possible to move the track in any position. It's not possible to neck the track. This was one of the options that we had. Okay. The trace that we can neck it or that we can actually shave the SMD pads. And it's both methods that we do not allow, which means that if I find such a situation on the board, it gets flagged, and you as somebody who's dealing with this data can go to your customer and you say, okay, I have several positions where we have this situation. What shall I do here? And there's actually only two things that he can say. Either he says, okay, I want to neck the traces, make them smaller, or shave the SMD pads. You know, and these are both the options that you both have. So we will obviously take a look at them. Maybe we have, because probably you saw we have, for example, we have 748, which looks like also quite a lot of issues. However, if you take a look at them, you will find them here. This is obviously flagged also as an error, because actually the bridge, according to my values that I have, should not be there, but obviously we must have a bridge. So it will cause violations of the rules that you have here, but they get flagged and you can see them and you can say, okay, this is exactly what I wanted. So actually these violations that you see here, they are logical. Okay, so okay, so what we still did not do is well, first of all, to repair the SMD pads and the traces. But maybe before we do that, it's maybe a nice idea to say, okay, I want to see, I have also this button inspect adjustments, where I actually can see if I press it, it will show me all adjustments that have been done. So over here, I have now nicely colored. Oh, wait. Nicely colored. I have all the, so the track movements, the, you know, the pads that have been shaved, you know, so you can see in one go how many elements have been touched by YELO. Okay, so that's actually quite a nice feature. So actually the whole job has been yellowed now. It takes around 10 minutes. The only thing that has not been done is the SMD pads and the traces. So if the customer now comes back to you and says, okay, yeah, well, yeah. So you can do something with this data. So maybe you shave the SMD pads. I mean, you can just, you can just say, okay, I tick those two. And I just say then I do a verify and adjust, and after this it will just shave the pads. We can also take a look there. So we have something over here, net compare found no errors, which is always very good. We like it a lot. So actually, and if we now look over here, this situation, and we have the original layer that we put in green, you can see now that the pads have been shaved. Okay, it's also because actually it says, okay, so this SMD pad, you would do it normally, so you would do it earlier than necking the traces. However, if the customer says I want to neck the traces, you just don't switch on the SMD pads and then the traces will be necked. Okay, so that's very simple. Okay, maybe you noticed that I skipped one method. So the via pad stacks. For this via pad stacks, well, I have a separate job. I just noticed, by the way, that before I told you, I wanted to show you a little bit about the preparation. So let's quickly do that before we go to this next job. So actually for the preparation, there's only two things that you must do. One is normally and you do it anyway, so it's really nothing that you are doing, but it's an automatism, let's put it like this, is that you enlarge your drill holes, because your customer sends you data for 1 millimeter, you will drill it at 1.1. You know, this is logical. Everybody must do this, and we have a little module for that called the drill tool manager. And if I say, okay, I load this drill file in my drill tool manager, I get a load of messages. It's like over here, because I did it already one time, so it's warning me that for all the tools, all the calculations have been done already. But you can see actually here that I set a certain function, so I can actually, if I have these drills, I can actually say, okay, I want to have this set as a component or a mechanical. You know, I have different functions here. And if I have these functions, this information will be used in YELO. So that's kind of automatically done already. The other thing is what we had this little button for an automatic markup. But we can actually, if we want, we can also see how the markup was done. So if I press here, I have a button for my markup assistant. It will open up a little module, and you can actually see over here that if I say now, okay, show me nice colors for yellow, that also over here you get your whole markup. Oh, let's type something here. I get my whole markup. I can see, for example, all my yellow pads are SMD pads, all my pink pads are BGAs or component pads, or so I can put my own colors and my own values in here that I can actually easily see how the markup was done from integrator. This markup is obviously needed because you have different repair methods for BGA pads and for SMD pads, but the auto markup normally takes care of all this. And this is actually the same button as you have also in the normal interface over here. So the run auto markup on the copper layers. Okay, so that's kind of the same. Okay, this is what I wanted to say about this job. So now let's go quickly to the via stack move job. Okay, so we have an example here. I can close the markup assistant now, so then we have some normal colors. Let's put it like this. I will hide this. So actually what you just see now here is a job. And actually what I now want to do now here is I want to see what happens if I say that, for example, the drill holes are too close to each other. I need to have more room there. Okay, so that's what we're actually doing now. I will just activate all the layers that I need. So that would also be the drill layer. I mean, that's actually one of the more important ones. And actually what I then just say is, okay, I do a verify and adjust. I do it now right away without looking what my errors actually are. But what you can see after a few seconds already is that the net compare found no errors, that there's no violations left, so everything has been solved. And now actually the question is, because when you see this picture, you say, okay, but it looks just like before. Which you could almost believe it. But if I now say, okay, I have my green layer and I put the drill layer in the green color, the original drill layer, then you can definitely see that there's actually 4 pads that have been moved around. Okay, so all those 4 pads have been moved. And the interesting part is that not only those pads have been moved, but also that if I move through the layers, I still have my original drill, but you see that also the openings in the copper plane, they have also been moved. Here have been moved, and also on the bottom side, I still have. This is still the original position where the drill hole is. So the green color is still the original drill hole. You see that everything has been moved. I mean, I can also maybe, because it's easy to see to this is the same layer now, so I don't and then actually you can see that the layer is it looks different, but obviously if you not look to the original but only to the repaired job, then it looks as it has always been this way. Okay, so this is actually a nice example for the via stack move. So well, actually, I think this is kind of the introduction to YELO. Maybe Sylvia, did you get some questions?
Yes, we have a lot of questions, and I picked some more interesting for the whole audience.
Okay.
So let us try to get as many as possible.
Okay.
What happens if a copper region is smaller than 0.2 millimeters in X, but bigger in Y? So I think this is basically the removal of copper.
Yes, it sounds like it at least. So actually it is, if I just, I take these values, I had here the minimum copper region size of 0.2, and we had this little dot over here or something like this, which was removed. Well, it's quite simple. It should be smaller in X and in Y. So if you have something that is 0.1 wide and let's say a millimeter long, then actually it will not be removed. It actually then will look at this value, the 0.08. So that means if it would be 50 micron wide, it would enlarge it to 80 micron, but it would still be a millimeter wide, but it does not get removed. No.
Okay, so I think that answered it.
I hope so.
Another one. Will it move impedance controlled lines?
That's of course a very good question. Yes, it moves everything that it gets in its way, However, I probably don't want them to be moved. I have a possibility to exclude certain elements from optimization. Now let's say we have a few tracks over here in the middle of the PCB. Let's just let's take the 2 bottom ones, for example. What I can do is I can select those tracks, like over here and over here. Okay, now they are selected. And I can put an attribute on them, and because we actually have an attribute to exclude objects. Okay, so also over here I have just put my object attributes window on the toolbar. I have different kind of categories, and as YELO is Y in the end of the alphabet, it's quite far down. And I have there an attribute named copper plane adjuster exclusion. Okay, and this attribute I need to set on these elements. So actually the only thing I do is add modify. Now it's been set on the elements, and that's it. So I can now, well, if I deselect the tracks, they will not be optimized anymore. You know, so that you can do pretty quickly.
Okay, I think we have time for another one. How safe is it?
How safe is it? Well, I mean, maybe you noticed already that it does a net compare. It always says at the end of the run, it says it makes a net compare and says there's no errors made, so no net errors made during the optimization. This is of course something that is very important. So yes, it's pretty safe. Pretty safe. Pretty safe, I would say. It's very safe.
Okay.
So yeah, so your net list stays the same, and I mean maybe in this well, in the same context, maybe I should also mention that obviously the YELO is not a module to completely reroute your design. You know, it's just you have your design, and it's being modified, and we try to modify it as little as needed. So what you cannot do is, if you start optimizing your data, what we already told also in the beginning, that the values that you use, that they don't match your PCB. Okay, so we already said something like, okay, you need to know kind of how big it is. Either your customer says something to you, or either you're like, okay, it's 100 micron board, so then you let it run with 100 or 120 micron, and you try to get it to the next level of security that you need for your production. What you cannot do probably is, you say, I get a 40 micron board, and well, I would like to have it on 300 micron. You know, that's maybe not a good idea. You know, and that's, of course, it doesn't have to do anything with security, but it's because the netlist stays the same anyway. However, yeah, well, it's just a better way to go. Let's put it like this.
While we are at it, let me show the new same net spacing to you. You find it in the Copper Adjuster menu, directly where the same net clearance was before. But now you not only have this single global threshold, which was working for everywhere, now you can use the object clearance thresholds for the same net. So for example, a pad to trace, a trace to trace, and things like that. Another one is the new automated adjustment repair for plated slots. Ring violation for plated slots are now reported and automatically repaired. To show how this is working, I will zoom a little bit more in so you have a better view of it. And I open the Copper Adjuster. I need to define a minimum ring, of course, or an optimum ring, or both. And I need the adjustment parameter of drilled pads expand. And when I let it run, I will get the backup layers. Of course, it will activate automatically the drill layers hitting active copper layers. And as we can see, we have solved 4 errors solved, and the net compare is without an issue. So, and of course we can see it is repaired completely.